take a look at covalent bonding in a little bit more depth, and we're also going to break covalent bonding into two different categories, polar covalent and nonpolar covalent bonds. So if you remember, we had talked about this previously, but if you have two nonmetal atoms that react together, let's start thinking about how they would react. So if I look at chlorine, it has 7 valence electrons. It's in group 17. All of group 17 has 7 valence electrons. And if I bring another chlorine atom next to it, which also has 7 valence electrons, how do you think these two would interact with each other? Well, if you remember, there's a rule called the octet rule. And the octet rule states that most atoms would be more stable if they have 8 valence electrons. So there's a trend where these main group elements are trying to get 8 valence electrons. How could chlorine get 8 valence electrons? Well, each chlorine would have 8 valence electrons if it could gain one more. So each chlorine is trying to gain one more. So neither of them wants to lose an electron. Like if this were a metal and a nonmetal, the metal could lose an electron and give it to the nonmetal. But in this situation, they both want to gain. So what are they going to do? They are going to share an electron pair. So these unpaired electrons are going to gather together. They're going to go into the center of these two Cl atoms, and they are going to be shared amongst these two atoms. So this pair is going to count toward each. So it's like this chlorine has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, and the same thing as the other chlorine. It's as if there is an octet of valence electrons around each chlorine because they've shared this pair. And this makes sense that this would happen for chlorines because chlorines are electronegative, meaning they would tend to attract electrons to themselves. So they wouldn't lose electrons, they would instead share. Okay, this is a covalent bond. Anytime you have a sharing of electrons, that is the definition of a covalent bond. And how do I know if this will form? Typically, this will be the case amongst nonmetals. And some metalloids would be in there too. There's even a couple of metal exceptions, but typically this would be between nonmetals. ClCl, HCl, H and O, OCl, so on and so forth. Okay, you can form single bonds where you have one pair of electrons shared. So for instance, each hydrogen here has 1 valence electron. If you remember, the closest noble gas to hydrogen is helium. So to have a full shell, hydrogen actually only needs to gain 1 more electron each to have 2 valence electrons. So hydrogens are going to be kind of a different kind of anomaly here, where unlike your other element, nonmetal elements, they're going to try to get 2 valence electrons rather than 8. So not really following the octet rule, but it is going to form a full shell. So here each hydrogen has 1 valence electron. If they gather their valence electrons in the center, they could share this pair of electrons, and it would be like each hydrogen has 2 valence electrons. And I just colored them differently to show you that this hydrogen owns 1, this hydrogen still owns 1, but they're sharing this pair, so it's as if each hydrogen has 2 valence electrons. Okay, instead of showing this pair of 2 dots, you can instead draw it as one line to show a covalent bond. If hydrogen and chlorine were to react with each other, this hydrogen has 1 valence electron, chlorine has 7 valence electrons. We could pull these unpaired electrons in the middle, and they could be shared as a pair. Hydrogen would now have 2 valence electrons, as if it has 2, and this chlorine, it's as if it has 8 valence electrons, both of them taking on the same configuration as the nearest noble gas, making them more stable. Okay, and I could show this shared pair as a line instead. And notice I still draw the unshared electrons as dots. So this chlorine, I can say it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around it, obeying the octet rule. So this line represents 2 electrons. Okay, you could also share more than 1 pair. So a double bond is when you would share 2 pairs of electrons. For instance, 2 oxygens together, they each have 6 valence electrons. So if they share 2 pairs, then they would each have an octet, or 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen, and same with the others. Notice that I did show different colors, showing that this oxygen still owns 6, or is bringing 6 to the table, and this oxygen still bringing 6 to the table, but by sharing these pairs, it's as if there are 8 around each, making it more stable. And just like how we could show a pair as a line here, I could show each pair as a line, and now I have two lines to show a double bond. And all the extra non-bonding electrons I still need to show. And I'm just showing you that you want to keep non-bonding electrons in pairs. So don't just have like 2 and then 1, 1. Keep them in pairs. And you could put 2 at the top, 2 on the side. They don't have to be shown as in this diagram, but they do need to be shown as pairs. And finally, you can also have a triple bond. A triple bond is where 2 atoms share 3 pairs of electrons. So let's think about what kind of atom might do that. Something that has 5 valence electrons like nitrogen wants 3 more to get to 8. So I could form 3 bonds. I could take each of these unpaired electrons, pull them in the center, and they could be shared amongst both atoms. This nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons as if we're around it, making an octet. And instead of 6 electrons, I could show 3 lines for my triple bond. And again, each of these lines counts as 2 electrons. So this nitrogen has 2, 4, 6, 8 electrons around it, obeying the octet rule. Let's look at how we can divide these covalent bonds into 2 different categories, polar and nonpolar bonds, and distinguish the type. So if you recall electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. So electronegativity is a measure of the attraction for electrons in the bond. And if you remember from chapter 6, electronegativity is the highest in the top right-hand corner of the periodic table, excluding the noble gases. So fluorine is the most electronegative element with an electronegativity of around 4, that's the highest number, and everything else is in relation to that. Oxygen's a bit lower at 3.5, hydrogen's a lot lower since it's all the way on the left-hand side at about 2.1. Okay, but you should know this definition of electronegativity. It's an attraction for electrons. So you can actually use the electronegativity value to reason about the type of bond present between 2 atoms. So bond polarity describes the sharing of electrons between bonds in a covalent bond, between atoms in a covalent bond. So we already know that covalent means a sharing of electrons, but that sharing doesn't have to be equal. One atom might attract electrons a little more than the other. And what is a measure of the attraction of electrons? That's the definition of electronegativity. So let's look at how we can use electronegativity to figure out what type of bond we have. So a nonpolar bond is when electrons are shared because it's covalent, okay, but they are shared equally between the 2 atoms. So in a nonpolar covalent bond, in order for these electrons to be shared equally, both atoms have to have an equal attraction for these electrons. And what is an attraction for electrons? That's the definition of electronegativity. So this is going to occur when electronegativities are equal, or in other words, when the electronegativity difference is 0. When will this always be the case? It will always be the case when I have 2 of the same non-metal atom joined together. So I have 2 oxygens, or 2 carbons, or 2 hydrogens. If I have 2 of the same exact non-metal joined together, then I will have a nonpolar covalent bond. So remember, covalent, most of the time we're going to be talking about nonmetals bonded together, and in this case they will be 2 of the same nonmetal. It could be in a diatomic element like N2, or it could be in the context of a bigger molecule where there happen to be 2 N's joined together in that molecule. That particular bond would be nonpolar. A polar bond, electrons are shared because it's still a type of covalent, but they are shared unequally. In this case, one atom is going to pull a little harder on bonding electrons. It's going to attract electrons more than the other and pull the electrons toward themselves. So it's kind of like a tug of war where one person's pulling harder than the other. It's going to kind of bring the rope closer to them. It's going to bring the electrons closer. Okay, so this is going to occur when electronegativities are not equal. So really, anytime the electronegativity difference is greater than 0. Now, there's some textbooks that define finite or exact ranges of when something's polar and nonpolar, but essentially anytime the difference is greater than 0, you have a polar bond, and the further from 0 it is, the more and more polar it is. So we're just going to say anytime the difference is greater than 0, you have a polar covalent bond. The further from 0 it is, the more polar it is. So this will really be the case whenever you have two different nonmetal atoms bonded together. Okay, so something like H and F, O and C, C and Cl. Now you might say, hey, are there any elements that actually have the same exact electronegativity? And there are a couple that do. And I'm not going to ask you to know them offhand. For this class, anytime you see two different nonmetals, you can assume that it's a polar covalent bond unless I actually give you the electronegativity values. Then I expect you to look, and if the difference happens to be 0, then it would be a nonpolar covalent bond. Okay? The greater the electronegativity difference, the more polar the bond is. Okay? How do you know, how can you indicate the polarity of the bond? So let's say we have HF. First of all, is this a polar or nonpolar bond? It's covalent because it's between two nonmetals. Electrons are shared because it's covalent, but it's shared unequally because I have two different nonmetals which have different electronegativities. One would be pulling harder than another. So this is a polar covalent bond. To know, in this polar covalent bond, we can determine which element would be pulling harder than electrons by checking the electronegativities. If you have a chart, you can actually look up values, or you can know that the electronegativity is highest in the top right-hand corner of the periodic table. So which of these is closer to the top right? Fluorine. So fluorine has the higher electronegativity than H. So it would actually pull harder on electrons. It would attract electrons closer to itself, and they would hover toward the F. Well, what are the charge of electrons? Electrons are negative. So if something is attracting electrons toward itself, it's actually going to start to get a partial negative charge. So we can actually show partial positive and partial negative charges with these symbols, which are, this is a little lowercase Greek delta sign. It looks kind of like 3/4 of an 8, but we can put this above whichever element is more positive or less electronegative. Okay, and we could put this partial negative next to the atom that's more electronegative, because that is going to attract electrons, which are negative toward itself, and it would have a slight negative charge. It's not a full positive and full negative, like it's not ionic. These are not ions, but it would be slightly negative or partially negative. So in this situation, I could put a partial negative above fluorine. I could put a partial positive above hydrogen to show that, hey, the fluorine's more electronegative. It would gather electrons closer to itself. Electrons would shift toward this. Okay, you can also do it with an arrow pointing in the direction that electrons would be moving or would be closer to. So you could show an arrow shifting the electrons toward the more electronegative element. So fluorine's more electronegative than hydrogen. I could put an arrow above showing electrons would move toward the fluorine. Okay. In a polar bond, electrons gather closer to the more electronegative atom. And these are just two ways that I could show that. A partial negative charge or an arrow toward the thing that's more electronegative. Okay, don't forget there's also ionic bonds, and that's going to occur when you have really large electronegativity differences, typically greater than 1.7. Some textbooks say 2.1, but really it's when the electronegativities are so different that the electron is actually transferred from one atom to another. One atom steals the electron. It's no longer shared. One thing gets a positive charge, it lost an electron. One gets a negative charge, it gained the electron. And this is going to be the case between a metal and nonmetal. So if you see two nonmetal atoms together, you can assume that there's a covalent bond going there. If you see a metal and a nonmetal, you could assume there's an ionic bond for the most part. Are there exceptions to this? Yes, but in general, this will fit most of your problems that you see. Okay, so something like NaCl, metal, nonmetal, it's actually the sodium has such a lower electronegativity than chlorine that the chlorine atom actually steals the electron from sodium, and that is why sodium gets a positive charge, chlorine gets a negative charge. They attract each other and form an ionic bond. The greater the electronegativity difference, the greater the ionic character. So for covalent bonds, the greater the electronegativity difference, we can say the more polar the bond. For ionic compounds, the greater the electronegativity difference, we can say the greater the ionic character. Okay, so just a summary, to distinguish the type of bond, first figure out what type of atoms are involved. Do you have two metal and nonmetal? Do you have two nonmetals? And then look at the electronegativity difference. So if you have nonmetal atoms, okay, then you're looking at a covalent bond. It will be nonpolar, meaning electrons will be shared equally. If your difference in electronegativity is 0, and that's going to be the case when you have two of the same nonmetal element joined together. It will be a polar covalent bond, meaning electrons would be shared unequally if your electronegativity difference is greater than 0. And again, this is just for nonmetals. Typically, two different nonmetal elements would be joined together, and that will tell you it's a polar covalent bond. And if you have a metal and a nonmetal, that's when you would have an ionic bond. Your electrons are transferred from the metal to the nonmetal. That your electronegativity difference will be greater than 0, and the further it is from 0, the greater the ionic character. Okay, so this is between metal and nonmetal. Take a moment and try this do now. Tell me what type of bond would be present, and I specifically put dotted lines to show that these are not necessarily covalent bonds. You'll tell me, is it ionic, polar covalent, or nonpolar covalent, and then answer questions 8 through 12 about them based on some of the definitions that you've done. Once you finish, pause the video, then once you finish, check your answers. So H and O is both nonmetals, two different nonmetals with two different electronegativities, so that's a polar covalent bond. F and F are two nonmetals, two of the same nonmetal, which would have the same electronegativity, so this is a nonpolar covalent bond. Na is a metal, F's a nonmetal, this would be an ionic bond. Cl is a nonmetal, O is a nonmetal, so it's covalent, two different nonmetals with two different electronegativities, that would be polar. Cu is a metal, O is a nonmetal, so that is ionic. Cl and Cl, two of the same nonmetal atoms, so they have the same electronegativities, this would be nonpolar, and these are both nonmetals, but different nonmetals with different electronegativities, this would be a polar bond. Out of these, which is the most polar bond? So I don't want to consider anything ionic because those would not qualify as polar. So I am down to considering all my polar bonds. Where is my electronegativity difference the greatest? If you actually had values, you can look it up, but you can also just kind of look at the trends on the periodic table. O is very close to the top right-hand corner. H is very far away, all the way on the opposite side. This would have the biggest difference in electronegativity. So if you don't have actual values to compare, you can see the placement on the periodic table. You're looking for something that is something that's close to the top right, something that's far from the top right, so that your difference is close, is further apart, is a bigger number. Which has the greatest ionic character. Now I'm doing that same thing but looking at the ionic ones. So Na and F would have the biggest difference because F is the most electronegative element. Na is very far away from it, all the way on the left-hand side of the periodic table. Which have electrons transferred, that's the definition of ionic, so pick all the ionic ones. Which have electrons shared equally, that's the definition of nonpolar covalent, so pick your nonpolar covalent. Which have electrons shared unequally, that's the definition of polar covalent, so pick your polar covalent. Take a moment and try this example. Pause the video and then check your work. HF, two nonmetals, two different nonmetals with different electronegativities, that would be polar covalent. Mg is a metal, Cl is a nonmetal, this is ionic, that 2 is there to balance the charge. And F2, two Fs, two of the same nonmetal joined together, that would be a nonpolar covalent bond. Take a moment, try the example, then pause the video and check your work. HBr, two nonmetals that are different polar covalent, therefore. Hg, you might be like, hey, I don't remember this. A, it's a metal. I could assume there's more than one metal atom present. What type of bond is present between metals? That is a metallic bond for review. NH3, two different nonmetals, polar covalent. CCl, two different nonmetals with different electronegativities, polar covalent. Ca is a metal, Cl is a nonmetal, that's ionic. Na is a metal. NO3 is is a polyatomic ion, so this would have ionic bonds between that. But between the N and the O, those are two different nonmetals. There would actually be polar covalent between there. So there's actually two types of bonds here, and that will be the case whenever you have an ionic compound that contains a polyatomic ion. Because Na and NO3 experience ionic bonding within the NO3 between N and O's. That's two different nonmetals with two different electronegativities. That's a polar covalent bond. So that's a little bit of a trick there. H2S, two different nonmetals with different electronegativities, polar covalent. Br, two of the same nonmetal with the same electronegativity. That's nonpolar covalent. Take a moment, pause the video, try this last example. Here I actually give you values for electronegativities and I want you to determine which is the most polar. Actually calculate the difference in electronegativity to do this. When you're doing that, always subtract the bigger electronegativity from the smaller so that you can compare all positive values. So you're just getting the absolute value of the electronegativity difference. So for CCl, I would get a 0.6 difference. I'm just doing the higher minus the lower. I don't care which element comes first here. Okay, for CO, I'd get 0.8. For CH, I'd get 0.4. And for NO, I'd get 0.4. So the bond that is most polar would be the CO because it has the largest difference in electronegativity.